Hey everybody, it's Mrs. Cassill. I'm going to go ahead and work through your crash forensic situation for you. So first thing I'm going to do is sort of reconstruct thinking through the problem here and figure out what all information do I have. So I know that two cars go flying off at an angle after a collision has taken place, and that before that point in time they had been driving perpendicular to one another. That's my basic scenario, right? This is the truck, this is the car, this is the truck afterwards, this is the car afterwards. So I'm given a bunch of stuff in the problem, right? So I'm going to go ahead and write down some of that. So the skid, the displacement of the car during the skid is 8.2 meters. Displacement of the truck is 11 meters. I know the angles that are right here, right? I know this angle and I know this angle. So I know that the angle for that skid after the collision for the car is, what does it say, 33 degrees? I'll try not to just state everything as a question as I look over at the assignment sheet. Then 7 degrees. I know the force of gravity, the weight on each of these cars is given. So the force of gravity of the car is 13,600 newtons. The force of gravity of the truck is big, 69,700 newtons. From those two things, I can figure out what their masses are, right? So this object, the mass of the car, right, force of gravity is equal to mass times the acceleration of gravity. So simple division there tells me that the mass of the car is going to be 1,387.8 kilograms. The mass of the truck is 7,112.2 kilograms. So again, that's just by taking this force of gravity divided by the acceleration of gravity to figure out what the mass is that would result in that force. They tell me that they can drag a tire that has, that the tire itself has a weight of, I'm going to write this down, of 130 newtons, and that to pull it at a constant velocity, it takes 100 newtons. Right, that's one of the other things that we're told in this problem. And that's for the car. I should say that this is only for the car. We're told that. So I can use that to figure out how much friction there is, because I know that that force of gravity acting downward, if it's not accelerating up or down, then it has to be equal and opposite to the normal force going up. And I know that the force of friction is equal to the coefficient of friction times the normal force. So the force of friction for the car, or rather if I want to figure out what the coefficient of friction for the car is, I know it takes 100 newtons to pull it along, equal to whatever the coefficient of friction is for the car, times 130 newtons, which is the force normal of the car. So when I solve for that, I get that the coefficient of friction for the car is 0.76, and there's no unit, it's just a coefficient, it's a number. And then they did tell you that for engineering or mechanical or manufacturer's reasons, that the truck coefficient of friction is equal to 0.7 to 70% of whatever the coefficient of friction of the car is. So that means that the coefficient of friction for the truck is 0.54 is our number that's there. Okay. I'm trying to think if there's anything else that's given that's important to know. They tell us that the car theoretically has an acceleration of 3 meters per second squared. That's how quickly it can accelerate. And I think that's about it. I think those are the things that we can deduce from here. We could do a few other quick calculations to get us started, but I'm going to go ahead and say those are most of our given values. And now our job is to think through our approach. How are we actually going to solve this problem. This is the part that when your teacher does it makes you feel dumb because we make it look really easy, right? The approach to a problem is where you actually show your real physics thinking. And I have lots and lots and lots of practice approaching these kinds of problems. I can look at them and I see what kinds of patterns there are. I know quickly what kind of situation this is, so I know what equations to use and what types of techniques I might need to use to solve those. Those are the things that come from practice. It's why practice and homework is good for you. For you, trying to figure out what to do, this is where you really show your thinking. This is why you can get a good score on a test item even if you don't get the right answer at the end, because you actually have to understand the physics of what's happening in order to approach the problem. The rest is just algebra or calculus, but that's, that's a different conversation. So when I look at this problem, I really see three parts, okay? So first thing I see is that we have this post-collision skid. So the first thing that's happening is there's this skid that's occurring. So that's the part that I can start with. When I think about what's happening there, I know that the force of friction is part of the skid. I know that there's a change in velocity during that skid because it's coming to a stop at the end of the skid. So my first thought is, well, the best approach there is that this is about how much work friction is doing to reduce the kinetic energy of this object. So I can use the work kinetic energy theorem to solve for a change in velocity. And if I'm coming to rest, then what I'm really finding is my initial velocity. How fast was I going at the start of the skid? So that's the first thing that I'm going to be able to solve for. The reason I'm doing that is because that velocity at the start of the skid takes me to the second part of this problem that you can see, which is the collision that's taken place, right? So we've got this but we've got this collision that's happening up here where there's been a transfer of momentum. So now I can analyze the collision, and I'll move my page up here as we, move on to the next little bit. But the collision, right? This is a conservation of momentum problem now. And momentum is conserved in all collisions and explosions. We're doing there's a little bit of physics magic here where we're going to imagine that there's no deformation of the materials. There's no destruction. There's no crumple zones. There's no chunks of the truck getting dumped off. There's no, like, while there's a payload in the truck that fell out the back door so that there's multiple particles. All of those things happen in a real car collision and are part of what a forensic investigator would need to include in analyzing this collision to determine who's at fault or what was occurring before the collision. We don't have any of that in here, so that means that there's basically no non-conservative forces. All of the energy that's contained in these two objects that are colliding is being conserved and transferred to them after the collision. So that's the little bit of physics magic that's there. If you were going to go and do this real thing for a job, you'd have a lot of that to take into account. And honestly, you'd use computer modeling for an awful lot of it. We would use statistical systems to model where does all that debris go and what does that tell us about the momentum before. But I'm going to analyze this collision because what I can do is this velocity that I found right here, that was the velocity at the beginning of the skid, is now the velocity at the end of the collision. So we're going to work backwards again to find the velocity before the collision. So that's the thing that we'll analyze next in this problem. The third and final part, and then I'll slide my page up, is these, sort of what's happening before the collision. And this is where we enter the legal aspect of this problem and the creative aspect. Are you the defense attorney? Are you a prosecuting attorney? Are you a police officer? Are you a manufacturer? Are you the guy standing on the side of the road who just did this and you're trying to figure out what to say? So the third and final part of this is basically to apply this to your scenario. Depending on what kind of question you were asked or which perspective you're going to take to attempt to defend, that's where you're going to sort of use what you've been given and what you've calculated here to determine who's at fault. This is where you might want to figure out things like, was the acceleration of the car really equal to 3 meters per second squared? You might want to figure out, was the very, very initial velocity of the car actually equal to 0? Or did that driver lie about coming to a stop at the red light? The velocity of the truck, they said that they were going 6.7 meters per second, that they were slowing down and braking. Is that true? Or were they also speeding? You might want to look up local traffic laws and figure out what kind of situation, you know, what the legal rules are for those types of intersections, or those types of roads. Oh, that is one more piece of information we were given. We were told the distance of the intersection was, I think, like 13 meters. Did I put that 13? I'm just double checking my piece of paper. Yeah, 13 meters. So from the stop sign to the point of collision, there's 13 meters. But anyway, you're going to try to apply this to your scenario and draw the conclusion that you need to. So your argument begins here. You will have all the information you need at this point, and it's up to you to choose how to use it. So with that, let's go ahead and start problem solving this thing, right? I'm just going to pull up my calculator so I'm ready to go. And then blah, blah, blah. So the very first thing that we're going to do is we want to do this skid analysis here. We want to figure out how fast were both of these cars going at the beginning of their skids, because that tells us how fast they were going after the collision, which helps us know how fast they were going before the collision. So part one here, we're going to analyze the skid, right? That's the first thing that we're going to do. So the work kinetic energy theorem, right, says that if work is done on an object, you're going to change its motion. You're going to change its energy. This is the thing that connects forces and energy. Really, those are two different ways of analyzing the same thing. Objects can move. How is their motion changed? So we know that work is a force times a distance, and that's usually in the direction of that that distance is the work that's being done there, right? We've got a change in kinetic energy, so we're talking about the difference between the 1/2 times the mass times the velocities squared. So, oops, that's my face. So we want to work backwards and solve for this initial velocity that's right here. Now there's a couple nice things going on, right? One is, if I'm skidding to a stop, then my final velocity is 0. So that really helps me out a little bit there. So I know that the force, I also know that it's the force of friction that's doing my work for me here, times my displacement is equal to negative 1/2 times mass times the initial velocity squared. I want to pause real quick, take a look at my AP equation sheet, just to see how they represent this in here, just to see. La, 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 la. Make sure I'm not doing anything different than they would actually do it. So here's the one thing, right, that we'll sort of highlight, and I'm going to do the workaround, right? Here is the work kinetic energy theorem on your AP equation sheet, and depending on how you've written it down in your notes from this year, you'll notice that it says parallel to the direction, the distance, I'm sorry, parallel to the distance that an object is moved for how much work is done. And then over here you'll see that really we're talking about the force times the distance over which that force is applied times the cosine of the angle between them. So work is a scalar quantity, but it can be negative because you can have work acting against your energy, acting against your motion. That's the case here, right? Friction is always going to act against our motion. So when we talk about this, if we were to throw in an imaginary cosine of 180 degrees, which is part of our official equation here, that becomes a negative number. So when we solve our algebra for this, our negatives cancel. Multiply both sides by 2, divide by mass, take the square root. And if you need to, this is one of those times, if you don't know what I just did there, pause and work through this. I'm solving this for initial velocity. That's what I'm solving for. Pause and work through it if you don't understand where I'm getting this. But I'm going to end up with the square root of 2 times the force of friction times the displacement divided by the mass. This is now my formula that I can use to figure out what happened to both of these moving objects. I'm going to substitute one more thing, right, which is I've got force of friction right there, but if I look over at my known and unknown quantities, well, I figured out what my coefficients of friction are for the road for the two different vehicles, but I haven't actually figured out how much friction there actually is. So let's go ahead and do that right now so that I can plug in a number. The force of friction for the car is going to be equal to my coefficient of friction, 0.76, times the normal force for that car, which is 13,600 newtons. So that equals 10,336 newtons. The force of friction for my truck is going to be 0.54 times my normal force, 69,700 newtons, which is equal to 37,638 newtons. So now I've got two forces of friction. So you can substitute the equation for the force of friction, which now that I think about it, I didn't actually write down. So I found that my force of friction is equal to coefficient of friction times the normal force. That's how I found those numbers. You can substitute that into your equation here and algebraically then just do one computation. But I'm doing it this way this time. That's what mood I'm in today. So here we go. I'm going to figure out what the initial velocity of the car is. It's equal to 2 times my force of friction, 10,336 newtons, times my displacement, which was 8.2 meters. Pulling that over here, from over here. That's under my radical, divided by the mass of my car, which was 1,387.8 kilograms. I'm going to plug that into my calculator. And I get that the velocity of my car is 11.05 meters per second. That's how fast the car was going after the collision had taken place. That's the initial velocity of the skid. I'm going to do the same calculation for the truck. 2 times the friction, force of friction of my truck, which is 37,638 newtons, times the length of the skid, which was 11 meters. Just that alone right there is why you don't play chicken with a big truck. They're almost always going to move farther than you anticipate, which could be where you're standing, parked, where a pedestrian is, you name it. And then our mass of that big old truck is 7,112.2 kilograms. And when I plug that all into my calculator, I get 10.8 meters per second. So those are the initial velocities of my car and my truck at the beginning of the skid. Those are my initial velocities. So thinking back to my approach, now I know how fast they were going at the beginning of the skid, which means I know how fast they were going at the end of the collision. So now I'm ready to do step 2. I'm going to work backwards, analyzing this collision to determine how fast they were actually going before the collision took place. So we'll come back over here. Little page break right here. So now we have to analyze this collision. This is where you have a two-dimensional collision. And we didn't do a lot of practice with that this year because we were all at home together when we did this unit. So you've got a challenge, which is you've got two objects that are moving towards one another perpendicularly. I guess from your perspective, they're going this way towards each other. And then afterwards, they go off in two other directions, neither of which are perpendicular to one another. So how do we account for the conservation of momentum when objects are moving in random angles after the collision takes place? The answer is basically that we want to find that momentum is conserved in the x direction and momentum is conserved in the y direction. That's how, because of how vectors work, right? The vector sum of the x direction and the y direction will tell us the total net momentum. So we can analyze the two dimensions separately to show that momentum is conserved. And if you really want, we can go through the vector addition at the end to show that that's true afterwards. You can do all of this vector stuff graphically. One of the things that students forget on some problems is that you can really carefully draw all of this out. You can take these velocities and these masses and work through this as a graphical problem. But math is often easier when you have crazy numbers, and where that way you don't have to depend on the accuracy of your ruler or your ruler skills or protractor skills to get it right. So if I need to find the momentum in the x direction and the momentum in the y direction, and I want to see that those two things are conserved, then I need to think about, all right, I've got two angled vectors after the collision. I've got velocities, one going at 33 degrees, one going at 7 degrees. So I need to break those momenta into their components so that I can analyze those separately. So I'm going to do a little bit of trigonometry right here. So let's do the car first. The car is flying off here. I've got a 33-degree angle. I know that this is the momentum of the car after the collision, and that momentum is equal to mass times velocity. So we've got the mass of the car times the velocity of the car. Well, that's easy enough for me to calculate. 1,387.8 kilograms times the velocity of the car. I found it right up here, 11.05 meters per second. And when I plug that in my calculator, I get a number which is 15,265? I can't read my own writing, you guys. Kilogram meters per second. I'm going to check it in my calculator just because, like I said, I can't read my own writing. All right, 1387.8 times 11.05. Not 11.5. There we go. Well, I got a different number that time, so let's double check that. 1387.8 times 11.05. Well, I wrote down a different number between the first time I did this problem and the second time. So that always makes you pause and double check your work, which is what I'm doing right now. I've got my notebook right here. So let's just make sure we've got our calculations right. That's right, that's right, that's right. Put that in right there. So I always like to see if I can figure out the source of my mistake too. I know, so if this part is boring to you, you can just fast forward through it. But let's see if I accidentally put in the wrong number. Would I get a different number? No, that's not it either. So I'm not sure. But anyway, let's write down the correct number. 1387.8 times 11.05. 15,335 kilogram meters per second. Now I need to figure out what my component vectors are, right? So now is where we're going to break these into components to find out how much momentum is in the x direction and how much momentum is in the y direction. So I'm going to have some vertical and some, pretend that's a horizontal line, but that's a right angle right there. One thing I should say is I'm going to use that this direction is positive. That's which way everything is moving, and that up is positive because that's which way everything's moving to. So that's something in case you're looking at your vectors trying to make sure you assign the right number there. That's a really important thing to notice. Okay, so now I'm going to break this into components. So that's just about using my sine is my opposite side. Cosine is going to be my adjacent side. So if I want to find the momentum of the car in the x direction. It's going to be equal to that total momentum of the car times the cosine of my angle. So 15,335 kilogram meters per second times the cosine of 33. And the momentum in the y direction is going to be equal to my momentum of my car times the sine of theta. Again, if you're not sure where I got those, pause and use your sine and cosine relationships based on this triangle to figure out where did I get this from. These are the kinds of equations that don't get written on your equation sheet for an exam, because if you don't have it memorized for some reason, I don't, I think through it every time. Sine 33. All right, so now let's go ahead and double check my numbers here. I've got 33, the cosine of which is that number, times 15335. So I got, for my momentum in the x direction, I'm just going to write it over here because I don't have room, 12,861 kilogram meters per second. Let's go ahead, 33, sine of 33.54 times 15335, 8,352 kilogram meters per second is the momentum of my car in the y direction. We're going to do the same calculation for the truck now. The only difference is that the truck will have different momentum, obviously, that we'll want to calculate, and there'll be a different angle right here. So thinking through the truck, I've got a much shallower angle because I've got 7 degrees right there. I've got my x component and my y component I want to find on my little right triangle that's here. Oh, I did much better drawing a horizontal line at that time. You think with graph paper I'd be good at it, but no. So let's find what our total momentum for the truck will be after the collision. It's going to be the mass of the truck, which is 7,112.2 kilograms, times the velocity I found up here, 10.8 meters per second. Just to double check my math, I'm going to do that in my calculator again. 7112.2 times 10.8 is 76,811.8 kilogram meters per second. Let's see. All right, at least that one I did right before. And now I'm going to use the same math to figure out what the x component and the y component of my truck are. So I'm going to take that momentum, 76,100, 811.8 times my angles here. I've got that again, the x direction is the adjacent side, so the cosine of 7 degrees, the sine of 7 degrees. And all things considered, I get 76,293.3 kilogram meters per second and 9,361 kilogram meters per second. So now I know the momenta of my vehicles in the x and y direction before the collision. So we're going to go ahead and take a look at that. I'm actually going to skip a page so that I don't get too much ink bleeding through my pages here. So I'm going to go ahead and write what those values are up here real quick. Just so that I have them to work with on the next page, but I better write them. The x component for the car is 12,861. For the truck, I guess for the truck I've got 76,000. 239.3. So just a little momentary. The car in the y direction and the truck in the y direction. The car is 8,352. And the truck is 9,361. All right, so here we go. All of the momenta in the x direction before the collision has to be equal to this total momentum in the x direction after the collision. So what we're going to do is we're going to find that conservation of momentum for the in the x direction, and this is where we end up with like a lot of terms getting written out. So we're talking about the final momentum being equal to the initial momentum in the x direction, and the same thing being true in the x direction as for the y direction. And now we need to add up all of the momenta before the collision. All right, so let's before and after. So for the car and the truck. So in the x direction before the collision, we've got the momentum of the car in the x direction plus the momentum before the collision of the truck in the x direction. That's equal to the sum of these two values after the collision, right? These are their momenta after the collision. I figured that out based on what their skid marks told me about how quickly they were moving. So this is going to be equal to the momentum of the car, 12,861, plus 7,620, or 67,239.3 kilogram meters per second. And here's the thing to think about. In your scenario, Mr. Incredible, the car, is driving this direction. He has no momentum in the horizontal x direction. So the car has an initial horizontal momentum of 0. All the momentum he got from the truck. So that makes this a really easy problem to solve. The sum of these two momenta all came from the truck. The hard part was breaking it into components. So when I add those two things together there, I get the momentum is 12861 plus 76. I guess I can show you my calculator. 239.3. So I get that the initial momentum of the truck in the x direction has to be 89,100.3 kilogram meters per second. All right. So that's my initial momentum. I'm going to go ahead and do the same thing for my, I'm going to put a little box around that though, so that's easy to find afterwards. I'm going to go ahead and do the same thing for the y direction now. My momentum in the y direction, the initial momentum of the car in the y direction, plus the initial momentum of the truck in the y direction. It's going to be equal to the sum of my post-collision momenta in the y direction, 8,352 kilogram meters per second, plus 9,361 kilogram meters per second. Again, you've got this scenario where the car is moving vertically and the truck is moving horizontally. So the truck has no vertical momentum before the collision. So again, this makes this a very easy problem to solve. The initial momentum of the car in the y direction is 8,352 plus 9,361. Whoa! It helps if I do the right numbers here. Hang on. So 8,352 plus 9,361. Much better. 17,713 kilogram meters per second. So I got two numbers now for the momentum. And here's where now we're going to finally get to a place where you can use this to find some calculations. We're going to solve for the initial velocity of the car and the initial velocity of the truck. We know what each of their initial momenta were. We know that their momentum is equal to a mass times a velocity. So therefore, if we want to know what that velocity is, it's the momentum divided by the mass. So let's find what the initial velocity of the car was. It's going to be this momentum right here, 17,713 kilogram meters per second, divided by the mass of my car, which is equal to 1,387.8 kilograms. And when I plug that in my calculator, divided by 1,387.8 equals, I get 12.76 meters per second. Let's find the initial velocity of the truck. The momentum of the truck was 89,100.3 kilogram meters per second, divided by the mass of the truck, which was 7,112.2 kilograms. 89,100.3 divided by 7,112.2 equals 12.53 meters per second. So, ladies and gentlemen, you now have evidence to use to determine what you think your court case should be. You know how fast Mr. Incredible was driving the car at the time of the collision. If he had come to a complete stop, could he have accelerated through the intersection? So this is where you would use that acceleration is 3 meters per second squared. You would use a UAM equation. Oh, and that the distance he's traveling now is 13 meters. And say, okay, is that how fast he'd be going with that acceleration over the space of 13 meters? Mr. Mater said he was going 6.7 meters per second at the moment of the collision. Turns out that's not true. So was he breaking the law? What kind of case are you going to build for these two people here now that we've solved this problem, right? Thanks, everybody. Have a great day.